Okay, now what I actually have here is a capacitor. If I crank the generator, now these things are wobbling around a bit, but it's not because of anything I'm doing here. When I crank the generator one way, it'll take the charge carriers, in this case the charge carriers are electrons, it'll take the electrons off of one of these, I call them, well, they're washers, but let's call them plates. Okay, say this is one plate of the capacitor and this is another. So electrons will be taken off of this one by the electric field in the wire, and the same electric field will deposit them on this one. Now, the electrons from here aren't going to go all the way around the circuit and end up here. It won't be the same electrons. The electrons you pull off of here will actually occupy a very minuscule length of the wire, actually of the clamp, and the same over here. But the electrons that get pulled off of here repel the other electrons, which in turn repel electrons onto this plate. And that's a capacitor. Now, this capacitor is totally ineffective, and among other things, it's not really very well stabilized. The plates are too far apart and they don't have much area, but that isn't relevant to the concept. Now, I guess the other thing I wanted to say there, get the thing back, okay. So if I do that, there is a current going this way and coming on to this one, current taking charges away from this one and depositing them on this one, or vice versa. And I hope you can see that. The way I've got my hand in the way, you probably can't, but you get the idea. Now we got to turn it, well, anyhow. Okay, there's a current, but there's no current in between the plates. Okay, well, if you know a little bit about electricity, you know you have to have a closed circuit. But not in this case, because there are electrons here, they can be pulled off and deposited here. You have an equivalent current between here, which is called a displacement current. Okay, we'll talk about that a little more, again with diagrams and so forth. Displacement currents come up in Maxwell's equations, which is why we want to talk about it. Now, here I have an effective capacitor, but it's not a parallel plate capacitor. Parallel plate capacitor consists of two parallel plates with charge carriers in both, so that you can move charges from one plate, take charge off of one plate and deposit charge on the other. This is a molecular capacitor which separates charge at the molecular level. Boy, that was interesting. Caused a little cramp in my pinky there. Okay, so I can transfer charge. Now, if I stop cranking, the charge is going to want to transfer back. And look at what happens. As the charge transfers back, it has the interaction with the magnet and the coil here. It creates an EMF that rotates the coil. And of course the thing slows down as we take charge off of this thing. But there's a demonstration, at least, that this thing is storing charge, which then wants to go back to where it was. So we separated charge. Charge is at one molecular end and taken away from the other. And now it's being taken, now the charge is being repelled from the end on which it was deposited and going back to the other molecular end of this capacitor. If you think of two plates, well, we do that on the board to make a little more sense of it. If I charge this capacitor, And the cranking gets easier as I go, for reasons that we might or might not discuss. Okay, you get this, and then I quickly disconnect the capacitor, and then I take my compass, run the wire over the top of the compass, get my hand out of the way, want that wire to be pretty close, and make contact here. There's a whole lot of response, which will decrease over time. It's already pretty much decreased. The capacitor discharged its charge very rapidly through the wire. That might or might not be important for our discussion of Maxwell's equations, but it was easy to set up, so we went ahead and did it.